Hello and good evening, everyone. I will be speaking and doing this presentation in English. And the topic for today, I believe it's one of the most interesting ones in the kind of new trends. We're going to speak about secure distroless OCI images. We're going to define, first of all, what is an OCI image, what is distroless, and what makes this combination secure by all means. We're also going to explore our approach to a new way of building what we have used to call Docker images via Docker files, and we're going to perform this action via YAML files. So we're going to focus on what the first presenter, Bojo, has talked about the containers and how nothing is secure in the container world. And at the same time, we're going to leverage this. We're going to look through some exploits and a lot of interesting stuff. First of all, I kind of reminded myself to introduce myself. And so I'm Victor Bonev, and I'm part of VMware Carbon Black team. Carbon Black is the team that manages cybersecurity inside VMware. And we kind of develop a lot of those solutions, which are the XDR, MDR, EDR words that you have heard about the previous presentations as well. I'm a senior developer, and I'm very happy to be here and discuss, gather opinion from each one of you, and hopefully you can learn something that's good and kind of the companies look for a lot. Let's go through the table of contents. So first of all, we're going to focus on what is OCI. We're going to define it. We're going to have a little bit of a brainstorm with all of you. Then we're going to speak about the OCI isolation. So we're going to do a crash course, which is 101 crash course, which we used to have at the university. Understand what is C groups, what is file system, and the container aspect. Talk about the change root, or C root, and namespaces. Then on the third chapter, we're going to show some exploits. And we're going to take a brief overview of the key moments that have happened in the past year. Of course, many things have happened. I'm not going to show all of the exploits, but at least I'm going to focus on the more interesting ones. And based on the previous presentation, we had a bit of chat about Alpine Linux. So we're going to talk about Alpine Linux, loved by many, hated by even more. So we're going to understand why is that the case. Then we're going to talk about distroless, what makes distroless image, and it is a lot of a interesting topic. And we're going to focus on the last chapter. We're going to talk about project Myclone, or Mycelion also. It is a project that we try to develop internally inside VMware Carbon Black. And it is our approach to solving some of the issues which we will outline during this presentation with all of you together. So let's talk about OCI. What is OCI? It is the Open Container Initiative. What you have all referred to, containers, Dockers, images, that is basically OCI, and that's the right way to refer to the container world. It is an OCI image. It's not a Docker image. It's not a Podman image. It is the Open Container Initiative. That's the standard way of how those things that we're going to talk about are based upon. So we're going to have a little bit of introduction. What is this all about? You're most familiar, personally, I believe that you're familiar with Docker. You have heard it during this presentation. You know what is it about? And Docker is very popular. Historically, it has been here for maybe a little bit less than 10 years. Yeah, cool. Well, kind of I guess that right. All right, so the next platform for OCI images, and I'm not going to refer as containers, is Kubernetes, of course. And I want to pay attention to all of you that those are totally two separate things. No matter that they handle containers in the same way, they're totally isolated. We're going to look why is that the case. First of all, if you follow, all of those containers behind the word container, there are a lot of services and software behind, and subcomponents. So we have to break down what this is all about. What is behind that structure that makes isolated environments unique, and why is it so popular? So behind Docker, there is a containerd, which is the container daemon, basically. Behind, that's the, basically you can refer to it as an engine, but it's actually a daemon that does the work for you to spawn and basically handle behind the curtains and in preparation for the next step. On the other hand, for Kubernetes, Kubernetes does not run on containerd by default. It used to have Docker shim, which was removed. It's no longer the case. And Kubernetes uses a different runtime daemon. It's called CRI-O, or you can also see it as CRI as well. That's Container Runtime Interface. And CRI-O was supposed to be a very lightweight, very performance-oriented container runtime interface. So there are more than this one, but we're not going to observe the rest. We're going to focus on those two. So what comes after those daemons? Of course, there is the Open Container Initiatives. So the Open Container Initiative sets a standard of what a container is. You can think of it as a protocol, even though it is not. But the same way of how, for example, TCP is defined in a big protocol, in a RFC. Yeah, it's very different, but you can think of it of an analogy. What makes a container? You have to have a checksum. You have to have a file system. You know, a lot of stuff that needs to be there in order so we can call a container understandable by containerd and by other container runtime interfaces. It's a set of standards that we have all agreed upon, and it's being continuously developed, updated. So keep in mind the containers of today's might be totally different from the containers of tomorrow, since all of those runtimes and container runtime interfaces keeps developing. New features come in, and that's why we need to certify pretty much every 3 years. This holds for Kubernetes as well. So in order to get a certificate and say I'm a certified Kubernetes administrator, I have to certify every 3 years due to the fact that everything changes. Pretty much everything. A lot of those things changes. Maybe not the core ones, but a lot of those stuff change. So what is after OCI? And what comes after OCI is basically run C. Run C, if I'm not mistaken, was first introduced in 2015. It was version 0.1. And this is the executable, or maybe executable is not the right word, but it's the runtime of how your containers are being run in the Linux world. And run C takes always a JSON configuration. If you have worked with containers, you have probably seen that you have to provide a Docker file in order to build stuff. And you have a lot of from, run, a lot of commands which are integrated. And those commands basically bundle different JSON files. It could be a JSON file for the networks. It could be a JSON file for your volume mounts. So all of those configurations, and pretty much in the Docker world, everything is in JSON. There's BSON as well. Everything feeds to run C. It basically run C executes all of those things out together as a big chain so that you can have what you have called containers so far. That's how it works behind the box. In a short summary, without the details, but this will do just fine for our demonstrations later on, the showcases which I have prepared for you. What I want to take from our view together, and if you have to remember something, is always question whatever you come across. That does not apply only to containers and Kubernetes, Docker. Whatever you use, always question how this works. And by no means, those are magical services or software which are unique. Something is happening, and if you don't know the answer to it, there is a very high chance that you will be exploited. Why you can be exploited? Due to the fact that you don't know the stuff behind it. Simply as that. This was stated by some presenter, I don't know who. So how it works. Understanding those pieces of software that do leverage the Linux kernel system and its components, alongside with its attributes, is the key. And as famously as the Din Djarin from The Mandalorian have stated, this is the way. And this holds for everything. It does not apply only to OCI, containers, or Kubernetes. You have to understand the concepts. So we're going to talk about the OCI isolation. What I'm going to do with our view is a crash course, 101. What makes sort of, you probably have heard again, why use containers in a company, or if you ask someone in person, well, they provide an isolated environment. And my question will be, oh, how so? So in order to understand how that happens, you might have heard, might have gone to the next level and probably heard, well, containers are a bunch of C groups and namespaces. But what I have witnessed is that the questions about C groups and namespaces also are unanswered for most part. So I wanted to show you, and I know that it might not be very visible, which I did my best. But the kernel feature, basically C groups or control groups, those are native kernel features. And they provide resources isolation. For example, imagine you want to run a process and you want to allocate only 256 megabytes of memory to that process. You can do this via control group. All of them resides under sys/fs/C group. What is unique is that you can create your own C groups. On most Linux distributions, there are already predefined C groups. Those are mostly your memory management, CPU, something that's related with network, something that's related with volume mounts, and you already probably map the features that Docker provide are not so unique, because on Docker or Kubernetes, basically what is exposed through a lot of its flags is actually goes to the native kernel feature, which is C group. Of course, containerd and CRI-O, which is a container runtime interface, leverage this via flag. And I'm going just to say out loud what is written below. So I can do a podman run or equivalent. Podman is different flavor of, it's a different software similar to Docker. I can do podman run with detached mode, with -d, and allocate the -m flag, which will limit my memory usage to 256 megabytes. And I'm going to spawn an Nginx and latest Nginx container. What it's going to do is create a separate C group under my parent process ID, which is podman, because podman calls containerd, and it already knows the namespace isolation, which we're going to talk in the next slide. The namespace isolation will be your container checksum. And you have spawned containers, you have observed that every container has a unique checksum, a unique SHA. So basically what you use through flags is controlling C groups, and basically you're controlling kernel features. There's no magic behind it. And in that case, if I simply echo the value, I will see that I have allocated like a 2,068,000 bytes, the equivalent in bytes for 256 megabytes. And it's present in my file system. So we're going to take to the next level and talk about namespaces. As you recall, containers are basically namespaces in C groups. So namespaces, what are those? Those are even more important. Those are kernel features for resource partitioning into set of processes. If you compare this to C groups, the C groups limits the resource usage, while on the other hand, the namespaces limits the resource a process can see. What do I mean by that? Imagine you go to a shell into some server, and just simply through that, I can execute, again, I will run a container, I'll do podman run with an interactive mode, again with the same nginx latest image, I'm going to execute a shell. This will basically, I'm going to use an old term, don't use it, SSH into the container, basically involve a bourne shell session, and I can list namespaces. So the command to do that is lsns. And I can see there are different namespaces, each comes with a unique ID. You can see it on the left column. And there is a type of namespaces. So we have now understand that there are namespaces and there are different types of namespaces. What is listed here? We have time, we have user, we have net, we have mount, we have UTC, which is related to the universal time. We have IPC, which is inter-process communication. We have PIT, which you have heard in the previous presentation. You know what PIT is, for sure. And you have cgroup. All of those namespaces have associated PIT, associated user, and what command has access to what namespace. So now we're going to the more a bit in-depth namespaces 2. And we're going to talk about what those kind of namespaces are. And it's very important to understand the namespaces so we can provide security for our containers. If we don't know that, we can't say that our container is secure. So we have mount, we have process ID, we have network again, inter-process communication, IPC, Unix time sharing system, UTC, user ID, and a control group. So what is all that means? Well, it all follows that those are simply attack vectors. Those are the primary targets of how you can exploit a container. And we're going to observe some of those exploits that do leverage this. Some of those namespaces, not all, but at least some. And you can see that there are a lot of attack vectors. Nothing, again, if we refer to the first presentation for today, maybe nothing is secure. Let's see. Containers do use namespaces to partition different resources. Imagine I want to run a podman with a BusyBox image. I'm just going to give you an idea what BusyBox is. BusyBox is one of the most lightweight images. It's not a distribution by any means. It's a type of a Linux image where all of your essential commands that the previous presenter have shown, ls, cat, echo, vim, netstat, whatever you can think of, IPSS, those are all bundled into one executable, which is kind of a greater set of those commands. So they're not built each one by one, they're bundled into one. There is BusyBox and there is another flavor you might have heard, it's called Toybox. Same principle. All of your Linux command that you have used during your terminal sessions are basically bundled into one executable, and once you refer it, there is something that's happening that's closely to soft links, and the soft links basically refer to different parts of the binary, so your command can run safely. So what we do here, that's what BusyBox is, and we execute a shell. What this does is it's going to create a separate namespace that will allocate my hostname. And you know that if you spawn a container, you see some checksum, or maybe you don't see checksum. It depends on how this is configured and executed through runc and containerd. But usually behind you, there is a hostname that's being created, network, different types of C groups, and a parent process ID. So I can list, now I'm into the container interactively, so I can interact from within. So I can type PS and see what my processes are. And currently there is not much, not much of it going on. I have shell and I have PS. Those are both root, owned by root. But what happens if I execute another shell? So this, if I execute another shell, this will basically do shell within shell. And if I do PS, I will see that I have two shells. So what is strange about this? That I'm in my child shell process, but I'm able to see the parent one. Observe here that my process ID is number 1. And if I invoke shell again, I have a different process ID, and this is the active one, which is 3. But then I also am able to see the parent process ID, which is in that case 1. That's the parent from which I have originated from. And even if I spawn a PS3, which is same as 3 for file system, but for processes, I'm able to see that shell is my parent with process ID 1. I'm currently running on the child process with pit number 3, and I've executed PS3, and that have allocated me process ID 11. So it is strange. We're going to see why. And before we go into the detail, I want to do with all of you some brainstorm. And there is a simple process inheritance. On the left, we have a cluster. It could be a Docker machine. It could be a Kubernetes cluster. It's some sort of a cluster where many nodes or containers can run, either through containerd or through CRI-O for Kubernetes. And I have basically spawned a very traditional showcase. I have my backend, I have my Nginx. It doesn't matter whether they run on containerd or they run on CRI-O. I have 4 containers. And I have my backend, I have my Nginx, I have front end, I have some metrics for logging, which that's how I love to do things. There is a separate container that's responsible for logging and doesn't interfere when I update. So imagine here that I have exposed for my Nginx port 443. And through Kubernetes, this is quite easy to do. You have either cluster IP or you have node IP for your exposure. There is another type of exposure, but we're mostly focusing on this ones. So for that case, that is a node port. Basically, your port is exposed and can be, you can interact with it. So my question to all of you is, what is the worst scenario that can happen based on that picture? You don't have to use the mic. If you have ideas, please raise your hand. Yes, so communicating with the inter-process communication, that's one. It is bad, but it's not the worst, but it's a great observation. Can we think about something else? Any ideas? Right? Precisely. Exactly. So this is the root of the problem and the worst thing that can happen. And there were cases like that in Amazon, in Google, in the major vendors for clouds. And what has happened is that you can escape outside of your container towards the cluster. And now, not only you have exploited, how I can do that? Imagine I have a vulnerability which I can exploit in Nginx. It's rare, it doesn't happen, I know, but let's say it's not Nginx, it's software that I have written. So I can exploit that. It's either, it could be buffer overflow, it could be use after free. Those are 2 of the most commonly used vulnerabilities that are being exploited. I load my reverse shell, and then I have access. But I have access only towards that container, so I'm isolated. I can't see what is the back end doing, what is the front end doing. I have access to that particular service. And miraculously, there issues and exploits that can allow me not only to control that container, but I can take control over the whole cluster. And this is run exactly through exploits that are targeted on C groups and namespaces. And mostly you can target container D, you can target cryo, and you can get leverage of the cluster. And now you do not control only your own data. The cluster can have thousands of nodes, and I don't know how many containers, maybe about 10,000 if it's a big one and owned by the enterprise corporation. And I can control pretty much everything. Doesn't matter. I have whole control. So I'm going to show you two of those exploits which do leverage Linux type of vulnerabilities. The first, actually, both of them were discovered last year. The first one is CV 2022-0847. The second one is CV 2022-1085. And what is a CV? Just so we are on common ground, that's the common vulnerability exploit. So notice the word common. Those are vulnerabilities that we know that do exist. There are many that we don't know that do exist. So what are those exploits? The first one, main cause, it is uninitialized pipe buffer flag variable. And this is a feature that's in the kernel. It's bug in the kernel that can be exploited. Basically, page cache is always writable to the kernel. Imagine I have to write a specific file, but I do it in such a way, and I can write a C program, which I can write a cache, but while writing the cache in a specific way, of course, I'll show you how this looks like, I can write a cache without the kernel checking for my permissions. So this came actually from a ticket. The exploit is called dirty pipe. You have seen it probably in the previous presentation. In one of those presentations, it was called dirty cow. So basically, that's the successor of that exploit. And what it does, I can write, for example, etc password file, and write it as a cache, replace it with my own password, elevate my privileges, become root, and then restore it from a backup. So you wouldn't notice that this file has been written down and then restored. There's no way you can guess that. Of course, if you don't have some kind of a audit monitoring of the actions that have been performed. The second exploit is actually related to the heap-based buffer overflow in legacy parse parent function. Again, it's a bug in the Linux kernel. And what it does is there are certain namespaces, and the certain namespaces have different aspects that they can interact with certain kernel features or kernel classes. An unprivileged local user, say I'm non-root, stating this clearly, I'm non-root, and I want to enable my capsys admin such that it opens its capsys admin is a Linux kind of definition of something legacy, but we trigger it so it can execute that legacy code. And what it does, it's open a file system that does not support the file system context API, and then it falls back to legacy handling where we hit that exact exploit. So it's something that's very similar what Bojo have shown in the previous, in the first presentation with the printer. There was a printer that was printing something that's for legacy, how you can send a GIF on your phone, and that GIF becomes PDF and your phone gets exploited. That's the same thing. We're triggering a legacy function that's, I don't know how many years old. Nobody knew it existed. So a fast recap. There is Docker, there is Kubernetes. Those are two different ecosystems. And they run on different daemons. One is containerd, one is cryo. And what I want you to emphasize on is that Kubernetes and Docker do behave differently in the aspect of the runtime. So what I'm going to show, I hope it's not very visible, but I can share the slides with all of you after the presentation. I execute a BusyBox image, and I do a PS. So I can see that my processes, I have 2 pits, both are owned by root, and I have 5.15.49 for my Linux kernel version. Then I do an unshare, and that's on the Docker provisioned container. When I do an unshare, that's basically detaching myself from another namespace, from the namespace and trying to create a new one. It says, oh, unshare, operation is not permitted. That's on the Docker. If I execute the same thing on the Kubernetes with a krun, K is just an alias for kubectl. Krun, interactive, same image, busybox, shell. It's the Bourne shell, it's the same shell. And I try the same command, unshare. It will run. So what I wanted to emphasize with this very simple example is that they behave differently. If you test your application in a Docker local environment and say, hey, boss, it's done. We can deploy it to the cluster. I've checked everything. There is no way this can get exploited. Kubernetes do things differently. Of course, this has been much improved with the latest version of Kubernetes. There are now filters that you can leverage, but you can state that explicitly. So you have to know what you're doing. So the lesson to take home is that they behave differently, Kubernetes and Docker. The next exploit that I wanted to show you is Dirty Pipe. Dirty Pipe is an exploit which is the successor of Dirty Cow. It's where I can write a cache to the Linux kernel without the Linux kernel checking for my write permission. So I can write pretty much anything, and I can override the etc password_d file. So what I'm going to do here, I have created a scenario where I use poundcat. Poundcat is a remote shell. It's very similar to probably some of you have played with Metasploit and Meterpreter. It's again a sort of a remote shell, and you can spawn sessions. Basically, it's very interesting. You can check it online. It's called Poundcat. It's open source. What I do here is I trigger and compile that specific exploit. It's written in C, and that it triggers the vulnerability. It's compiling. It says compiling Dirty Pipe exploit, attempting to run, completed successfully. And what I do, I check my ID, and I have become root. Initially, I was not root, but then once I do that exploit, I have elevated my privileges. And you don't know how widely spread that exploit is. That was fixed in the later versions of Linux kernel 5.15.29. So it was fixed in the last 7 months or 8 months. Imagine how much it will take for the industry to catch up and update. Not everyone updates their kernels regularly. So everyone makes them vulnerable. And if we don't know, again, simply by attacking the kernel, we can elevate privileges, become root. Now imagine what will happen if we find problems and combine different exploits, so we can escape outside of this container and reach the cluster with root privileges. It doesn't matter whether our container is running with non-root. We can elevate our privileges. The next exploit, it's pretty much a heap buffer overflow. And for this, I have prepared an image. I have uploaded to the public Docker Hub under VP Bonev /BSides-attack1. And I create a pod, which is called BSides attack1. Then I SSH or spawn a bone cell session interactively and check what my processes are. So I list my namespaces here. And the idea about this hack is that I can change my namespace. So if I do captch print, which is capture, basically capture the current, the bounding, and the current IIB namespaces, I can do unshare /URM, And basically, unshare URM tries to detach from the current namespace and spawn a new namespace. And now I have elevated the capsys admin privileges for which I was supposed not to. I was outside of that namespace. I didn't have access to it. But simply by invoking unshare, I'm able to change my content of visible namespaces and namespaces which I can reach to. So that is one way of container escaping. That was fixed in, I believe, quite recently. But it's one attack that you can work, and some vendors, which I will not name, have suffered from it. So the tools that I have used, I always want to state my software, which I've used for that presentation. The first one is ASCII Nemo, for which I recorded my terminal sessions. It's very useful. I recommended it. It's you'll remember the name because it's an acronym for ASCII Cinema. So it's ASCII Nemo. And the second one is a bind reverse shell. It's called Poundcat. You can check it out, and you can also watch the introduction from the guys that did invent that remote shell. They're great. I mean, I've learned by watching that session alone more than I have learned in 5 years, and the session was 50 minutes about remote shells. So another important point that I want to make during this presentation is that security moves with time. And what is secure today will not be secure tomorrow. What you have observed so far are kernel exploits, those two exploits that I have shown you. And I want to again emphasize that the kernel, kernel.org, is one of the most async software ever developed. This is watched by so many developers, so many eyes are developing on this, including our company is contributing. But it's so big that a certain developer takes a certain class, there is a subset in that class for that feature, and there is just one little fragment that he's focusing on. And that's reviewed by many. This is one of the most secure software ever written. And it does have exploits. Yeah, despite, it is at the root of everything. It runs everywhere. You'll not find something that does not run Linux kernel. Even now, the new versions of Windows are shipped with Linux kernel, and they support that. It's a very safe piece of software. It's present everywhere. Now, for a moment, imagine how many common vulnerabilities other softwares could possess. Think of a moment about this. Because if one of the most observed piece of software have such vulnerabilities, and those are criticals, and of course, the industry tries to catch up, patch regularly, etc. But the other software is not on such strict monitoring. Usually you can have a developer pushed code, and there could be buffer overflow that could be used after free. And it's a lot more dangerous, at least in my opinion. No, not only that, but this software can be added on top of public images, Docker images or container images or OCI images. They all refer to the same thing. So the next time someone asks you, oh, I wanted to run that service very quickly, you probably will just go to download the first public image that's available on Docker Hub. I'm not saying that you do it. Many developers do that. And those images are full of vulnerabilities. Even there is Snuck now running on Docker Hub, which is their scanner. And you have approved and certified, verified images and repositories. It's still like tons of vulnerabilities everywhere inside those public images. Don't trust them. So the next topic I want to bring on this table is Alpine Linux. And my question towards you is, who currently uses Alpine? Okay. You know this would be bad because this presentation is not about Alpine, right? Okay, so yeah, Alpine is loved by many and hated by even more people. Why is that the case? Usually, the process towards coming to Alpine Linux goes through a size comparison. And I have shown just an example showcase. I want to build and provide basically an image that can run Go and build Go, whatever that the case is. If you build Go, then it could be a larger image in size. But I wanted to just provide a comparison about how the choice to pick Alpine is usually done in companies, not only enterprise companies. One manager, and that brings us to our previous talk, one manager checks, oh, that image about Debian, it's 1 gigabyte, that's a lot. How can we bring this down into a smaller image? And developer checks, oh, you know, I saw this Alpine Linux. They pretend to be pretty much small in size. Let's give them a kick, see what happens. Usually the people don't know what the 4 other words mean below that graph, meaning distroless, Scratch, Advanced, BusyBox, and Scratch. So I will explain those to you. Distroless we're going to talk about in the later slide. Scratch is basically, you can refer to it as a no, so it's a no image. It's empty. BusyBox I have explained, but I'll recap. That's an image that's pretty much Scratch with the essential Linux commands, so you can still echo, cat, ls, sort of those stuff, that commands that you use day to day. And you also have Scratch Advanced, which is advanced Scratch, but it's still no. So Alpine, why do people pick Alpine? Yeah, you have package manager there. You have APK. And APK can install very easily additional software on top of your image. I can do APK add and install, I don't know, Vim, GCC, GNU compiler, whatever I want, quite easily. Understanding how those pieces of software leverage Linux kernel, system components, and its attributes is the key. And this is the way, as the manual have said it. So I will speak about why I will personally never use Alpine. The main reason for that is that Alpine uses Muscle, which is an implementation of the C standard library. So it doesn't use the traditional glibc or the GNU C library. It uses Muscle. What Muscle does is it's more lightweight, it's performance optimized, so we thought. It's faster and simpler than glibc, but it's used, it's used by other Linux distribution. Glibc is used by other Linux distribution. Muscle is kind of specific to Alpine. So what is the backfire of using Muscle in Alpine? Because Alpine size reduction strategy is based around Muscle. So they're compiling the whole stuff into a different lightweight C library, which is obfuscated. It doesn't present with the same features. So the first thing that happens is native code hell. Software compiled against Muscle runs only on Muscle. What is meant by that? If I use Alpine during my CI/CD pipelines and I do compile native code, I have to run that code against Muscle. libc will be immediately segmentation fault. So I'm limited. If I'm stuck with Alpine, I'm stuck for life. I can't run that on other C library. That's only for native code. We're excluding Java. We're excluding other types of non-native interpretational tech stacks. Talking about native code: C, Go, Rust, etc. Next thing, Node.js, and that's JavaScript. Node.js calls to the Muscle compiled native code via Node.gib. So Node.js can call native code via Node.gib. Basically, you can access your C classes from JavaScript. And that's done through a library which an awesome person wrote through an NPM. It's called Node.gib. Falls big time outside of Muscle. Again, we have the same problem, and we're referring to the native code hell. So if I compile Node.js native code on muscle, I have to run it on muscle. Otherwise, I'll get memory hell. I'll get segmentation fault immediately. I'm not able to run my software or my service outside of muscle. The next thing is very, I believe it's one of the most interesting, at least for which I have come across, and it's DNS hell. So it's funny, so bear with me. Muscle by design, so we're talking about the muscle C library, does not support DNS over TCP, which means that usually you wouldn't give a damn about this, right? You just would notice, and the chances to read that randomly anywhere is pretty much zero. It will just explode at some point. And the way DNS are being resolved, the responses and so forth, for muscle is done through UDP. It's not through TCP, it's done through UDP. UDP is limited to 512 bytes. And that's, you know, by their standards, they said, oh, that's enough. You wouldn't need more than 512 bytes, which kind of refers to the Bill Gates famous saying, who would use 4K of memory or something like that. And of course, there are cases where you need more. And I will tell you a story about a case which we had running Kubernetes. And again, a manager came, says, oh, well, you know, I talked with other managers, they use Alpine, and we should use Alpine as well. They're great. They stated that everything runs lightweight. It's lightweight, it's fast. Awesome, let's do it. Let's onboard Alpine. Though, the cluster starts throwing unknown host exceptions. And basically, seems everything, it was seemed like we were breached. We were exploited big time. We got unknown host. And we had our network, so we verified this, but nothing worked. Everything stopped working at some point. And this was the fact due to that Kubernetes and the internal DNS name resolutions, they use tremendously long DNS names. So you have something that's, I don't know how many, it can get tremendously long. And 512 bytes is not enough. And you just not get your DNS resolved in Kubernetes if you use Alpine. And who would have thought about this, right? What are the chances? And it was just a big no-no for us once we had hit this. And gladly we hit this in an isolated environment, but at first it was like, oh God, we got hacked. We didn't know what was causing this. And we understood that it was DNS, but we thought it was DNS hijacking. And someone took control of our DNS. That's what we thought. So we're going to talk about what could be a successor to Alpine, and it's distroless. So what distroless is, and I want to, again, ask who have heard or used distroless. Great, okay, so 2 people, excellent. So distroless is not a buzzword. I know that this buzzword talk has, you know, come across a lot of us, but it's not a buzzword. It's the right approach towards working with containers, especially in the Kubernetes ecosystem. So the initial concept is developed by Google, and you know, they started with some of the rules, what distroless is. They started, you know, basically the same approach where your manager can say, oh, let's use something that's smaller in size. But they were opposing this and state, okay, we're going to develop our own stuff. Maybe usually it fails, you know. The chances to succeed developing your own ideas have a great chance to fail, but they succeeded. Their concept was right. So what distroless is, the name refers that it is a Linux image without the distribution. But it's not the case, right? The distroless image means that you don't have any command or anything that's present. You only have the things that are needed so you can run your application. No matter if that's Java, if it's native code, it's Go, whatever. You only have the capabilities of the software you truly need. And of course, you can think of that brings the size tremendously. The base distroless image is like 3 megabytes or even less. So there are no package managers. That's why it's probably not understood by many, because you want to work with package managers, or so we thought. There are no shells or any programs. There's no less, there's no more, there's no Vim, there's no cat, there's no nothing. You cannot shell. Just, it can run your executable. That's it in most cases. And it's perfect for Kubernetes clusters. Why is that the case? Because we are limiting the attack surface on our clusters. So when we're packaging our services in a distroless image, and we're bundling this, we can ensure that we are only shipping the essential stuff. We don't have overhead on our traffic cost. We are not, striking down our ECR repository if we're on AWS by pulling tremendously huge images. Yeah, maybe if you're doing something that's very specific, you might, this might not be the right fit for you, but this is currently something that's loved by many, that approach. It's perfect for KNet clusters. And what Google did is it provided different set of distroless images. So you have static Debian, base NoSL, Python, Java, Java 11, Java 17, Node.js, etc., etc. They come in 4 flavors. You have non-root, debug non-root, and latest. And of course, distroless image does differ in size. The static file system is around 2 megabytes. If you add some additional stuff like certificates, OpenSSL handling, etc., and of course Java, if you add Java, Java is a giant, it will get, the size will increase. But relative to the things you need, it's still very small. So size is relative. And I wanted to demonstrate this with something that we basically monitor our images and how they behave internally through plot. And I've picked some of the images which are publicly available for Go, reading top to bottom, Go, Node.js, Nginx, and we have developed our own kind of a distroless version of those images, which I will call VMware/Go, VMware/Node.js, VMware/Nginx. Those are not public images, though. If you search them, they're only on our private registry. If you observe the total CVE count on the public images, like for Go, there are 461 present on March 6. In comparison, we only had 8. That's how we have limited and addressed the attack surface. And it's the same version of Go. Same goes for Node.js, same goes for Nginx. And if you observe at the end of the graph, we addressed them with time, and we're very close to 0. And those include high, medium, and low as well. So not only critical. So some of a VMware insight, and I'm going to wrap it down. We wanted to create a symbiosis between package managers, because usually when you're creating a Docker file, you usually do a run commands, and those run commands install different stuff. So it's usually how a Docker file looks. It's one from statement, something that your image is based upon, which someone else developed. Then you have a big chunks of a run statement, usually in one block, to be in one layer even. So it can be a little bit lightweight. And there's so many limitations with Docker files that we wanted to kind of do then maybe something that's better than Docker files. And again, leverage the package managers. So we ditched Docker files, and we switched to YAML syntaxes. And it was our plan to save big bucks, as we wanted to reduce our cost of goods sold and basically our cloud bill on our cloud vendor, and overall technical debt. We wanted this to be very easily maintainable, because if you developed images, container images, you would observe that if you want to bump the parent image in fixed address vulnerabilities, etc. You have to build, synchronously the rest of the images. So it could be, I don't know how many built operations and constant bumps. So it's one parent, another parent, child, the child of a parent. So it gets like, I have to build 10 images if I want to have a proper inheritance. We wanted to have a far more secure-oriented approach, flexible, built, and dynamic images. So something that we refer to Project MyClone. And it is a inside name, something that we plan to develop. It's a new way to build distroless images. If you search on the internet about this, nothing will pop up, something that's internal. So there's no advertisement in this one. So something that we understood is Docker files are in the past. And there is one Docker file that's we used to have, and we still maintain due to several reasons, but we wanted to switch from Docker files to YAML syntax. I know that it's not very visible, but we wanted to build an OCI image against a YAML. And what this does to us is that we are no longer relying on storage for our images in a container registry. We can do this runtime. And if you have watched or seen Kubernetes in action, you can do a pod specification, and you can specify an image, and there you can specify like a repository, which is an OCI repository path towards your image with the appropriate tag and so on. You can just include a YAML file, which is local. And you don't have to pull, I don't know how many megabytes of image each time. And you do this runtime, it's very quickly, it's like that. And basically it calls your package managers. It supports Dagnified, DNF, YUM, aptitude get, APK, even though we don't use it and we don't recommend using it because it was breached. And yeah, usually you just handle the package managers accordingly. So we wanted to that was the first iteration. Then the next iteration, we wanted to use a Cloud Native Foundation emerging project, which is BuildPack. And BuildPack.io. So what BuildPack.io does is it can look into your repositories and create a Docker file specification. It's a tar at the end. Your image is just an archive, but it can create the right capabilities in order to build or run that specific image. Imagine I have a C++ repository with some C code in it. I throw a bunch of stuff in it, and I can just execute BuildPack against it, and that will create the necessary recipe so I can create my image without me observing what's in there, without adding additional libraries and so on. It does it for JavaScript, for Rust, for Golang, for Java, C++, C, whatever you name it. So we combine this, and we don't create a tar archive, but we create a YAML specification which can be broken down, and you can inherit this, leverage this, separate it into different pieces, and you can, of course, develop on top of it without bundling each time separate image upload and so forth. So the process is, it's very unique in an aspect, at least I haven't seen anything so far. And Flow usually uses Co, which is the Co build. So if you go to GitHub and says Co, it's something that's used in Go to produce a minimalistic tar archive. Basically your file system for your image, and that's consumed by the container runtime interface. There are two separate streams that you can pick. Either you do a build or you do a runtime, because images that do requiring build are totally different. They're usually bigger, they're not meant for production. Runtime images, on the other hand, meant to be, only the things you need, so you can run this in production. So we have build, we have run. We have build packs that does feed what needs to be added in terms of packages. And we have a process where those packages are managed by different package managers, and you don't have to use run or anything like that, what's used to be in the Docker files. Docker file is pretty much outdated by now. So each package is broken down into capabilities, and that's again a feature which it's not something that we have invented, but we have improved upon. So if you observe upon Nginx, if you do yum install Nginx or aptitude get install Nginx, there are different capabilities inside that image. So Nginx is a bundle of its subcomponents or capabilities, and we're making a compatibility match matrix where we're matching only capabilities that we do need for our specific package. What is the end result? Okay, so what's all this doing? We're creating an image that's minimum in size, easily built, and easily maintainable. And in comparison, you don't need a container registry. This is Artifactory, Nexus, Hub, ECR in Amazon. You just do things on the runtime. The CI/CD flows usually repository cross-referenced via centralized repository. It executes a child job prior to the build. A reproducible YAML spec is created for that required image for that specific repository, which is using build packs. It consists of 2 YAML file specifications, one for build and one for runtime. Pick your own thing. We just do both of them at the same time. Our images are signed with cosign and with the appropriate timestamp and built on the fly. No artifact storage, no OCR. And last but not least, just for a comparison size-wise, image size is drastically lower. Like the public Nginx image is 56 megabytes. And by using all this novel approach, we managed to bring it down to 3.8 megabytes. That's fully functional Nginx that you can include in your a Kubernetes cluster for how your load balancing works. And you can fed it to your K9 Kubernetes definition, and you can cross-reference it with a timestamp and so forth. So that's all I had, guys, and thank you very much for your attention. And do you have any questions?